we're asked to analyze the motion of an object that rolls 120 centimeters down a ramp, starting from rest, starting at when the clock starts at t equals 0, and at position x equals 0, moving in the positive direction. So the first thing we calculate, and we need to have this pretty much as a reflex. If we know our displacement and the time it takes, we immediately want to calculate the average velocity. Everything else in the scheme that we're using right now follows from that. Okay, so we have the 120 centimeters, the 4 seconds, and we'll call the 120 centimeters delta x, x being our position, and the 4 seconds is delta t, t being clock time. So the average velocity we get by dividing the displacement by the clock time, or the change in position, x's position, change in position is displacement. Could be positive or negative depending on the situation, but we're given that in this case the ball moves in the positive direction, so the displacement is positive 120 centimeters. We do that division, we get 30 centimeters per second. We express our fact that the velocity starts at 0, that is, that the ball starts from rest at time 0 as v of 0 equals 0. Okay, at 0 seconds, the velocity is 0 centimeters per second. And I could have put 0 seconds here, 0 centimeters per second here to be completely consistent. Maybe I should have. It's not a bad practice. Often we'll indicate that the velocity at t equals 0 by v sub 0, but that's not always the case. V sub 0 is generally the velocity at the beginning of whatever interval we're analyzing, and that interval doesn't always start at time 0. So maybe that, that would certainly apply here, but we're going to write it this way to be consistent with the way we want to write things in the future. Well, we immediately then understand, and we need to know this right now, this is something we've been talking about for over a week, that the one condition I didn't give you is that the velocity changes at a constant rate. That is, that the velocity versus time graph is a straight line. So that here's your velocity versus time graph. It's a straight line, and we know, and it's a straight line segment that goes from t equals 0 up to t equals 4 seconds. After that, we no longer have the straight line graph. Maybe we hit a wall, maybe we fall onto the table, but our velocity is no longer then, after it gets to the end of the ramp, is no longer guaranteed to be changing at the same rate. You won't have the same straight line. So the straight line is only a line segment that goes from the t equals 0 to the t equals 4 second instant. It stops here, unless we have other information that indicates maybe it keeps going, maybe the slope changes for some reason. This is all we know, though, so this is all we draw. And we know that the average velocity occurs at the midpoint of that graph. You can prove that using the fact that average velocity is the integral of the velocity divided by the time interval. And we've talked about that. And if you don't know the calculus, well, you just kind of accept this. There are ways to argue it. We're not going to worry about that right now. So at the very middle here, you're halfway along the time, so you're 2 seconds. And you have the average velocity, 30 centimeters per second. Now, what's the velocity at this point? Well, this triangle here is similar to this little triangle here, so you have the same rise. The rise from here to here is 30 centimeters per second. So this rise is 30 centimeters per second. So from the t-axis up to this point, it's 60 centimeters per second. It represents, this altitude here represents 60 centimeters per second. Okay? Now we don't want to think double this, because if the initial velocity isn't 0, we don't do that. We think similar triangles. The rise here is the same as the rise here, so we can figure out how much change there is between here and here. And we go from that. Okay, so the slope, and we automatically do all this. We want to know the slope, we want to know the area underneath this well, within this trapezoid. Now, this is actually a triangle, but I'm going to generalize the notion of a trapezoid, a graph trapezoid, to include trapezoids that have zero height, zero graph altitude on one side. But this trapezoid, or in this case triangle, has a slope that's equal to rise divided by run. If you go from here to here, your run is 4 seconds, your rise is 60 centimeters per second. You divide that, you get 15 centimeters per second squared. Now that is what we call acceleration, but we're not really using that term right now. The area is the average altitude times the width. This goes back to the definition of average value as the integral divided by the length of the interval, also to the fact that you can construct easily a rectangle whose area is equal to that of this region. Just cut the region here, take this triangle, turn it upside down, and here it is, and now you've got a rectangle whose altitude is the average velocity and whose width is the time, represents the time interval. So that, for this figure, for a straight line graph, you can prove that without using any calculus. But if you're in the University of Physics, you want to keep reminding yourself of the calculus connections. Generally, calculus is pretty easy, at least in the first half of the first semester. But there are insights that you get if you know calculus that you might not have gotten in your course, because of course you're in the booming, buzzing confusion of trying to learn calculus. We want to make these connections. Good way to deepen your knowledge of the calculus while you're learning the physics, and then the calculus really enhances your physics too. Okay, anyhow, the average altitude times width, 30 centimeters per second times 4 seconds, 120 centimeters, and it darn well better be 120 centimeters, because that's the displacement. And that's what the area represents. Why is that? Because this is the average velocity, the average altitude or midpoint altitude represents the average velocity, and this represents the duration of the time. Average velocity times duration of the time gives you this, because this divided by the interval, length of the interval, gives you the average velocity. Very simple. Okay, so now from constructing this figure, we know that the slope is 15 centimeters per second, the vertical intercept is 0 centimeters. So what's the equation, what's the velocity as a function of time? Well, v of t is slope times t plus the vertical intercept. That's the basic, one of the basic ways you get the equation of a line. There are others, and we'll probably use them, but for right now, that one's going to work just fine. Okay, well, that just comes out then, slope 15 centimeters per second times t. Okay, now the next task, and we do it based on this function, even though that's not the way the problem is stated on the worksheet. Based on this function, we're going to construct a trapezoid corresponding to the interval from 2 seconds to 4 seconds. Now we've already got that trapezoid, right here it is. 2 seconds to 4 seconds, there's our trapezoid. So we don't need to construct it from the function, but sometimes we will, because sometimes all we know is the function and we won't have this information.